Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this fifth project in the series of 5 projects that we have been working on, we took a break in previous video where we talked about support vector machines intuition. So this video is kind of a combination of both. We'll be working on a project which was the fifth project in the series, and we'll also be looking at support vector machine implementation on a real world data set. So the objectives we have are twofold. One is we'll build a classifier to that classifies the scale of a forest fire. So we'll create a categorical variable for that, and then we'll do the prediction first for the burned forest area, and they'll move on to classification. So the video is divided into 3 parts. First, we'll read data. It's a very small file. Then we have a regression and followed by classification. Many thanks to UCI machine learning repository for providing this file, and many thanks to the authors from the University of Minho, Portugal, for making this data set available in as a free source. I'll put the links to the description and the data set in the description so that you can download the files. So forest fires, as you already know, is when the forest is actually on fire. And so it's important to predict forest fires to avoid damage both to the forest area, and also if there are residential areas around the forest, then avoiding damage to any of those areas. So for predicting a forest fire or predicting how much area a forest fire could burn is based on several data points that are collected, and some of them are listed here, which is fine fuel moisture code, duff moisture code, drought code, initial spread index for the wind, build-up index, and all of that goes into calculating the fire weather index. We are not going into the details of what each of these indices, how they are measured or how they are calculated, but just to give you an idea of what these are, because those would be used in the data set that we are about to see. So the data set, if we look at the data set, this is how it looks like. The first column does have column names in this case, and the data set is surprisingly small, 518. But word of caution there, even though the data set is small, does not necessarily mean that it does not necessarily mean that it's an easy data set to work with. So we'll see about how and why that is the case. So we have this month and day, which are categorical, and the area, which is the last column, that's our target column. And these are the descriptions for what each of those columns indicate, some of which I've already mentioned in the previous slide, such as these abbreviations that are listed here. So with that, the data file, once you download the zip file, there are 2 files in it. This is the forestfires.csv that we saw, and this is the forestfires.name. Now let's get into Jupyter Notebook and see how we can work on this problem of predicting burned area in a forest. Here again, I've mentioned the link for the data set, and also the description of the data on the UCI machine learning repository website. And also we have the citations here, both for the authors and for the repository. These are the libraries that I've added here. We'll need additional libraries such as SVM. So from Scikit-learn, import SVM. So we have those, and these are the versions of the Python that I'm using right now. Now for the data set, So let's create some columns. Sorry, it's cells here. So first, as usual, we'll set the path to the file, downloaded file, users, and the file that I've set is on the desktop. So I'm navigating to that folder, forest fire, and then we can read the file. So this would be pd.read underscore csv, and then we have path plus file name. So there are two files in there. We need the forest fires.csv file, and header is equal to 0 because that file does have a header. And as we read it, we can print the shape df main.shape, and we can get the first few rows. So df main dot head, so you can see what's in the data frame. So we have around 517 records, 13 columns. One of that is a target column. So we have 12 features that we start with. Now, I tried a couple of iterations working with this data set, thinking that this would be a good small example for a linear regression or a linear classifier problem that we have been working, and what those projects were focused on. And I soon realized that this particular problem was out of the scope of linear methods, and so waited until getting the support vector machines part introduced, and now we can use both linear as well as the support vector machines. So we'll start out with using a regression. So we'll try to predict the area, but then uh, we also create an additional variable so that we can use work with this data set as a classification problem also. So to make that happen, we'll create a new feature or a new column, not feature but a new target column, which is which is fire scale. So fire scale, we can specify if based on the area, if the fire is small, no fire, small fire, large fire. So let's do that now. Df main area dot apply lambda x, and here we'll first use the no fire. So if the area is 0, we'll set it as no fire. So this is equal to 0, no fire. Else, if the area is, else we call small fire, small underscore fire. If the area is greater than 0 and the area is less than 2 hectares. I'm not sure exactly what are called small fires or how what area is needed for it to be classified as a large fire, but in this case, just for this project purposes, I'm classifying the small fires as those that have an area up to 2 hectares. And with that, else, and the last one is large, else we'll call them as large fire. And when we run this, now when we look at the df main, so let's print df main.shape and df main.head, and we can see that we now have additional column and we have one extra column in the shape. Now, as you've seen in the data set description, the area is the data in the area column is skewed. So if we look at that, plt dot hist, and this is df main dot area. Here we can see that this is indeed skewed. We have a right hand tail on the right hand side. Let's say bins is equal to 50 if we try 50 bins, and then say plt dot show. And so here we can see that there is a long tail on this axis on the right hand side, and therefore we'll see if we can use log to kind of bring this uh, um, to push this higher side on towards the right side. Next, let's look at the uh, how many records are there by month. Are there more records only for a month and few for less? Because that will help us understand how the data set is. Although it's a small data set, if there is any inbuilt variability in there, we can find that out. The df main dot group by, we can do a group by on month column and then count the number of records in the month column itself and see and then plot it. So plt dot bar t dot index and t. So here, as we can see, the month of August and September has a lot more records. So this is a 175 and this has 175. So around 200, 300, 350. So more than half the records are for just these 2 months. And uh, if there are more fires in these two, then maybe these 2 months will dominate. So we may have to see how we can upsample the remaining months to get a better prediction. And at the same time, we can also look at the data by day. So Monday, Tuesday up to Sunday, and see if there is any difference. So as far as days are concerned, the data looks pretty even. Although there are some less data points for Thursday, Tuesday, and Wednesday, it's not as less as what we had for months. So now what we could do is we could try running the regression first and see what we get, and then I'll show you why upsampling is important in this case. So uh, if we get started with first converting the categorical columns month and day to ones and zeros. So we'll do that now. So convert to ones and zeros. So for this, we'll use x is equal to, so for that, what we can do before doing anything, we'll create a copy. So d is equal to df main dot copy. We have a separate data frame there. And now with that data frame, we can split the features and target. So d dot drop, and here we'll drop the column of area because that's the numeric target, and we also drop the fire underscore scale column because that's the categorical column that we created from the target. So that's the x we will get, and then for y would simply be the area column. And so that is good. This is, now we are working on regression here. So let me write down here, let's give a heading that this is regression and this is part 1. So let's do that. This is part 1 and this is again the regression. Okay, now for getting the dummy columns, we'll use the same method, pd.get underscore dummies, and we have x and then month and we have day column. So this should get the dummies. So now if you look at x dot head, we should get yep. So we have this additional day Friday and then month October. So those are created and we don't have those columns anymore in the data frame. So while we are doing that, we also need keep track of our original columns because we need to separate the numeric columns and these one-hot encoded columns later on when we do the standard scaling. So what I'll do is create another list columns for scaling. So these are the columns for scaling and those would be, let me copy this. So if we call x dot columns, what we need is just these columns that are there. Okay, so those are the columns that we have that we need to scale when we before we do the fitting. Now once we have that, so now our data set is ready to proceed to the next step, which is you split the data set and then uh, split and then scale it. So for regression, we'll first have x train, x test, y train, y test is equal to train underscore test underscore split, and this is x or y, and shuffle is equal to true, and there's no classes, so there's no stratify here. Now because we had this particular issue of skew right here, what we can do is let's limit this axis. So for plotting, so plt.xlim, we go from 0 to maybe just 100, and maybe not, how about 200. Okay, so or the better way would be df main, and here we can specify area and area to be less than 100. Okay, so now we have data points only up to 100. So that's how it looks. If we go down to 20, so that's the data set. And with log, what we can do, and this is also suggested in the description of the data set, we can use np.log and take a log of this and add 1 to this. So now when we it is there is still dominance of this bar at 0, but then the other data points seem to have moved here. So if we add another filter, so let's say, let me copy this, and we can say that this should be greater than 0, then we can see that that's the data. And here if we copy this, and or maybe let me just copy this filter part right here, and if we add that and add a parenthesis there, now if we look at this data, we see that it is now moved towards somewhat normal distribution and the tail is not there. So that's the idea of using the uh, x plus 1 log x plus 1, and so we'll do that here. So np.log, and this is y plus 1. So that's the change we are doing to the target variable for modeling purposes. And now we can print this. So x train dot shape and x test dot shape, so we know what the shapes are, and we see that it's around 387 130 for each of those. Now that we have split the data set, we can now go ahead and split it further for scaling purposes. So here we'll do split again for scaling, and for this we have x underscore we'll create x underscore train underscore original. So these are the original columns that we need to scale. X train dot lock, and we'll use the list that we created earlier, which is this. And so it'll pull only these columns, and it won't get any of those one hot encoded columns in there. So the next remaining one hot encoded, we can put it in another variable, x train categorical, and here we have x underscore train dot drop, and here we can drop all the columns that we are using up above here, and that would be along axis is equal to 1 for column. So we have that, and now we can run the same for the test. For test, I'm going to change the names here, so TEST for test, and the columns again would be similar to what we have in the train set. So instead of doing this, what we can say is x underscore train dot columns. So get me only those columns. And again, here instead of saying drop and this, we can say dot lock x underscore. This would be x underscore train underscore categorical dot columns, and this would be x underscore train underscore original dot columns. So we are using these columns here, and then we are using these columns right here. So this is for the test, and that's a typo there. So this, I think we are good here. So let's run that. Now once we have split those, we can now use StandardScaler. So StandardScaler, and if you remember from previous video, scaling is very important when we are working with support vector machine. So preprocessing dot standard scaler, and okay, we need to fit this on the train set. So scl dot fit x underscore on x underscore train underscore original. So that's this data frame, and then we can transform on the train and test now. X underscore train underscore original is equal to scl dot transform x underscore train underscore original, and then x underscore test underscore original is equal to scl dot transform x underscore test underscore original. So with that, we can now combine the scaled data frames that we get here. So to combine, we need to combine this with this. So we have to get the categoricals in there. So x underscore train is equal to np dot concatenate, and here we specify the list x underscore train underscore original, and then np dot array. This needs to be converted into an array now, because the output of StandardScaler was an array. And so with that, we specify the axis is equal to 1. So that's for x train. Now we need to do the same thing for the test data test array. X test is equal to np dot concatenate x test, so test, and then again we specify the np dot array x underscore test underscore category, and so that's the data we have there. Now once that is done, we can print the shapes again. Print x underscore train dot shape, and then x underscore test dot shape. So because we need to make sure that these numbers match the numbers we started with. So we run this, and there's a error. So let me run all these cells again. Okay, so the error is name x underscore. Oh, right. So that's my mistake. Or there should be an I in there. So let's run these again. and we have 387, 29, 130, 29. So we are good there. So the scaling is done. Now we are the modeling part. So I will fit regression model here. So uh, regression model, and so for this I'll start out with simple linear regressions. Reg is equal to linear underscore model dot linear regression, and we have reg dot fit x underscore underscore train and y underscore train, and then we have the prediction part. So prediction, you have y underscore pred is equal to reg, and this is dot predict, and we have x, we are predicting on the test set, so that's there. And then we need to score. So for scoring we have MSE, which is matrix dot mean underscore squared underscore error, and this is based on the y test and y pred, and similar to, and we can print that. So MSE is equal to np dot round MSE, and we just need the 4 decimals. Along with MSE we have other variables that we can look at. So the next one is we can look at the MAE, mean absolute error. So let's add that ABSOLUTE, and mean absolute error. And then the last one we have is the R2 score. So let's go ahead and add that R2 underscore score, and again add the R2 here and R2, and this is MAE. So now when we run this, we'll get the output scores. Before we do that, let's plot the predicted and the actual value. So plt dot plot y underscore pred, and sorry, y underscore test and y underscore pred. So we know how they deviate from each other. So scatter, okay, and maybe add alpha there. Alpha is equal to 0.5. Now when we run this, let's see what we get. So as you can see, it's not a good fit. The R square values closer to 1 are considered good. So we need at least something above 0.7. However, here the R square value is much low. Uh, so, and if you look at the plot of the actual and predicted values, so let's add a title, the x plt.x label. Here this is y underscore test, and then plt.y label. So here we have y underscore pred, and we can see that the actual values and the predicted values, no, there's very there's no good comparison, no good correlation between those. So the predicted values are way off, and therefore if we think of this, that I also tried other linear regression models on this, and I couldn't get a better score with linear. So you could try all the models that we have been using in the past 4 videos, run them on this data set and see what you get. Now one alternative is to see if the support vector machine works here. So what I can do is copy all of this and paste it here. And now, so let's regression. So let's call this linear regression, and let's call this model. So we have that, and now we'll look at support vector machine and see if that makes any difference. So this is SVM regression, and so let's preface that with model and call it a markdown. Okay, now for support vector regression, we need to use svm.SVR. So that, and here I've already looked at what values could work. So I'm going to put them here. Kernel, this is RBF. So default value for C, I think it's 1. Then kernel is also RBF default. G- Gamma value, we'll set it to auto. And then max iter to so that it completes the it converges, we'll set to 5e4. And cache size, this is what I was talking about in the previous video. So if your computer has RAM that you can allocate to this particular run, you could increase that. So default is 200 and you could specify a higher RAM. So I'm specifying 1 GB RAM for this run, and the rest everything stays the same. We have xtrain, ytrain, and the scores and the plot. So let's run this. So again with SVR as well, it's not able to do a good job trying to predict the regression values. Now, one of the reasons that got me into thinking why this could be the case is, if you look at this data, there seems to be a very big difference in how the data is laid out. So what we could try doing is we could upsample these data points and see how that affects the results. So maybe because we have the first point was we had the target that is skewed, and now we have the varying number of data points for each month. So, and in here we see that this is August and September. So the months of summer, May, the April, May, so those have very few data points there. Maybe the fires are during those months. We can actually check how the data shows us those fires. So if you use df main dot group by, and we group this on let's say the fire scale, uh, or let's say if we group this on yep, let's just group it on fire scale and count. So let me do this. Count scale this on month and then look at fire scale. Dot n unique on, okay, and if we add fire scale in there and then count fire scale, so here we can see that the month of August and September, so this is August, so we have 71 large fires, and in September we have 76 large fires. So the month of May and April, which are those hot summer months, there are very few data points. There's just 9 data points there and only 2 data points here. You would think that the summer months would have more data points, but that's not the case. So let's go ahead and upsample this. So what I'm going to do is go back up here and upsample the data frame. So for upsampling, uh, or we could upsample it here, doesn't really matter. So d is equal to df main dot copy. So that's the same copy that we created down there. And once we have that, let's run that and print d dot shape. So that's the original shape we have. Then for month in uh, the month column, so dot unique here, if we take, so what we need is uh, the months that are August and September, we keep them as is, otherwise we upscale it. So m not equal to, so m not equal to August, and and m not equal to September. So if the incoming month m is not neither of those two, then we can scale it. So d and then d of month, and this is equal to m. Then what we want to do is sample. So how many records do we need? So these are around 175. So let's say if we get around 175, would that suffice? So let's start out with 175, and replace is equal to true, because uh, we don't have enough data points. So we have to pick a row, sample it, and then put it back in the data frame so that we can sample it again. pd.concat, and then what we want to do is add that new data set to the existing one. So axis is equal to 0, and with that, then you can print the shapes. So print d.shape. This is after the upscaling is done, and then while we are at it, we can go ahead and see how the distribution looks when we plot it. So t is equal to d dot, so this would be the same plot that we have above here. Let me copy that and paste it here. Now when we run this, we have 200. So we are plotting df main, so sorry about that. We need to plot just from d. So because we ran that cell, we need to run it separately now. So now we can see that as compared to before, we do have about even number of records in all the months. With this new data, let's see if it makes any difference when we run the regression. So we go through the same steps again. It's just that now we have more number of data points to work with. And so our initial model R2 score was around minus 0.14, and let's see what we get. So let's run this. Now we are up to 0.25. We can go and run this one. So this is now up by 0.4, and we can see this line that some of the values seem to be predicted correctly. So the upsampling part, what I'm going to do is, if we try to upsample it even more, if we go even a step further, so let's say if we upsample maybe 300 data points. So what we need to do then is go back up and run these cells again. And once we have run those, we can get on the df min, which is a new from df, and run this. And with those new, we can have this data set. Now the importance of August and September has gone down. So we are introducing artifacts in the data set as we are upscaling it. So depending on the problem that you're trying to work, it may or may not be advisable to upscale. And even if you are trying to upscale, you want to be cognizant of how many rows you're adding in. Does that change the picture of your original data set? So here what we are trying to do is we are going beyond what the data set already had, and we are introducing more of the same data over and over again to see if that makes any difference on the regression. And as you can see, with more data, we do see some increase. So we have gone up to R square value of 0.659, so around 0.6. So the takeaway message from this could be that if the data set is smaller, maybe you may not get a better fit models. You need more data to be able to fit to get a predictive model. Before moving on to classification, I just wanted to try one more option here, and that is using scaling. But then what we want to do is use just the records that have non-zero values for the area of forest area burned by the forest fire. So for that, we'll set a filter here, df main, where area is greater than 0. So with this filter and without upscaling, let's see what output we get. So that's a regression for. So as you can see, our dramatic difference between the values for linear regression. Here we can see that r square value is 0, almost 0, and here in the scatter plot we can see the predicted values are everywhere, so there's no trend we can see. Ideally you would want to see a straight line between those two, and here with the SVR, let's run this again. Okay, in here also we see the same effect. So not much of help if we remove those data points. Now again, if we continue with the same filter but then upscale the data set, so I'm going to add that line here so that we can run through this loop of upscaling and comment this out so we don't update the data frame D again there. So when we run this one and upscale it, we have that, and then we run through this all over again, and let's see what we get. So now as you can see, when we removed the data points that were all zeros for the forest area burned, we may not we do not have the information of which areas did not, or we cannot predict if the forest we cannot predict zero burned area for a forest. So that's the drawback there. But then as you can see, the r square value jumped to 0.72. So that's one way. And another point to remember here is that it's not always the case that you'll know what the target value is for a particular features set, so for a particular row. In this case we know that, and so we were able to filter out the rows that were 0. But if you do not have that target column, then there's no way you are going to know what columns predict what area of fire, what area the forest fire burned. And so in that case you have to stick with the original data set that we did in the very first run, and then conclude that there is not enough data to successfully predict the area of forest fire burn with just the 500 records that are there, out of which when we train we just have around 300 in the train set. Now with that, let's now move on to the classification part. So I'm going to create another heading here, part 2. Okay, so for classification, so this is classification. For classification, we are going to try first without upsampling any data and see what output we get, and then we'll see if we need to upsample it. We have dfc is equal to df main dot copy, and So now we can look at dfc dot fire scale dot value underscore count. So we can check how many records are there for each of the classes. So for no fire, we have 247 class records. For large fire, we have 208, and for small fires, we have 62 records. So that's not too bad. So now we can split the data. So what we can do is, because we are repeating more of the same stuff that we wrote above here, I'm going to copy all of this right up to here. So copy that and then go down here and paste all of that. So uh, if there are any changes, we'll edit those. We don't have to type every single line. Okay, so now we have this, and now we can split this. So dfc dot drop, so we drop these two columns, and then for dfc we get the fire scale from y. Once we have that, we can get the dummies for month and day as before. Then we'll call this xc instead of just x. We call this yc and xc also. So we'll run that, and we run that here. So that's the data frame we have. And now we can look for the column. So x column, which is where we want to look for the original columns. So those are right there. Yep. So that is good. Let me run that as well. And here now when we are doing the split, here we need to change this to xc and yc. So, and because we are doing a classification stratify, we can set this stratify to yc, and we can check the shape. So let's see what the error is. Concatenate can only concatenate the string. Okay, so that's that. Shuffle is equal to true. Yc. So the ends test split. So that's our x. That's our y. And oh right, because we are in a class now, we don't need the log there. Okay, so we have that original data set. We do the scaling, and we combine the data after scaling is done, and now we can perform the fit. So we'll start out with linear. So this would be model, and this is logistic regression. We'll use logistic regression first and see how it does, and then we'll do the svc. CLF is equal to linear underscore model dot logistic regression, and here we have max underscore iter is equal to 1e7, penalty is equal to elastic net, and then we have solver is equal to SAGA, and L1 ratio is equal to 0.75. No particular reason I'm choosing this. We could also use the default values. So this is clf.fit x underscore train, y underscore train, and then we do the prediction. Y pred is equal to clf.predict. This is x underscore test. We predict on the test set, and then we get the scores. So accuracy ACU is equal to matrix dot accuracy underscore score, and this is y underscore test y underscore pred, and then we can print the accuracy. So ACU is equal to np dot round. So this is ACU, so we need maybe 4 decimal places there, and after this we have the confusion matrix. So matrix dot confusion underscore matrix, and this is again y underscore test, y underscore pred, and we have just cm. So we can run this now and see what output we get. So we get a classification accuracy the accuracy of 0.47. So there are a lot many misclassifications. Now we can run support vector machine and see what output we get on this. So for this, I'm going to have to delete this entire row and type svm.svc support vector classifier, and here we specify c is equal to 1, that's the regularization term, kernel is equal to rbf, and then gamma is equal to auto, and then we have max underscore iter is equal to 5e4. That's because I tried smaller numbers and it gave an error warning. Cache underscore size, I'll set it to 1000 again, and rest everything else stays the same. We run this and we get an accuracy of around 0.5154. So that is still less than what we have, what we would expect from this. So one option then again that we haven't introduced in this yet was checking for the stuff such as zero variance, etc. So let's try that. So here we can add checks, and in these checks we'll look for zero variance, and so for xc is equal to xc dot columns, and so the columns within this we have xc dot var, and along axis is equal to 0. So if that should be greater than 0 values. So we can look at the print x dot shape before and then print x dot shape after. So index is not callable, so let's check why. We have right, this should be and this is there. Okay, so this caused us to drop 500, and we dropped several records here. So let's run this from beginning. Okay, right, so now we are good. So we have 517. This should be xc, not x. That's the reason why. Let's run this again. Okay, so we have those records, and then we can check for the correlation, collinearity, and for this we have x underscore corr is equal to xc dot corr, and we take a square of that, so coefficient of determination x underscore upper is equal to x underscore corr dot var np dot upper triangular, and then here we have np dot ones x underscore corr dot shape, and then we have k is equal to 1, and finally we have dot as type np dot boolean, and we are looking at r square value to be say greater than 0.7. So drop underscore column is equal to, we have for column in x upper dot columns, if any x underscore upper column, if that column is greater than 0.70, then what we want to do here is get that column in the list and we can drop it later on. So xc is equal to xc dot drop, and this is going to be xc and drop underscore call axis is equal to 1. So so here we are getting the columns from, we don't need this. So here we are getting all the columns from this data frame, from this set, and then we drop the columns that we don't need here, and we save that in there. So if we again print the value or the shape of x, c dot shape, and then print the shape again after x c dot shape. So here we so we didn't drop any columns, so that is good. So these two sections didn't make any difference. Now finally, one last thing that we can try is upscaling. So let me copy exact same code that we have up above and paste that for the classification part right here. So maybe here, and we because we are saying this as DFC, might as well change the name here, DFC, and this is all DFC now. A DFC and this is DFC. If we run this, and here before we run this part, okay, we do have the DFC dot chip. So we now have 3,517 records. So we can run those through here, and let's see what we get. We'll skip those two for now, or run through them. I suspect, yeah, that's what I was suspecting. There will be high collinearity, so those columns uh, could get dropped anyways. So this XC, let me run this again. Okay. I thought it would get dropped, but it didn't. All right, so that's good. So we have these many records. We run through this, scale it, and then we have the, so for logistic regression, run that again. Okay, so now it's okay. So there's some mistake there. Probably I didn't run it. So here we have the logistic regression that is at 0.73, and we have the SVC at 0.83. So although not as big difference as we said it was before, but still 10% difference is pretty substantial. So that was it for this video. I hope in this video you got a new experience and understanding that because a data set is smaller does not necessarily mean that it could be easy to use to get either a prediction or a classification task done. As we saw, the data set was small, but then there were a couple of gotchas in there. One was the target variable was highly skewed. The second was the data or the instances or samples were also imbalanced, highly imbalanced between different months in a year. And so those two factors combined together greatly reduced the prediction accuracy for classification tasks as well as for the regression. So the workaround in this case that worked was upscaling and then using log for the target variable. And just a word of caution, when upscaling, you want to be you want to make sure that it does not change the original picture of the data set. If possible, you want to get additional data and add it to that data frame rather than upscaling the data that's already in there. So that was it for this video, and this was also a video as a as the coding part of the previous intuition video on support vector machines, and completion of the 5 video series for projects uh, up to linear for linear models up to support vector machine. In next video, we'll move on to newer topics in supervised learning and see how those methods work, and look at some new fun projects where those methods work in their own special way, where other methods may not be able to work as good. So if you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. And if you are interested in some other projects that you'd like to try, please let me know. I'm also thinking of starting a series on reviewing data sets. I don't know if you'll be interested in those types of topics. Please let me know in the comment section below. Thank you.